today we're going to take the mole one step further and use it in what we call stoichiometry. Now, one way to think of stoichiometry in terms of like baking is if you're trying to bake cookies, you're going to need a certain amount of sugar, a certain amount of flour, a certain amount of eggs to make a dozen cookies. So the process of baking is really figuring out what quantities do you need of those substances to make the amount of cookies that you want. Stoichiometry is the same kind of idea in chemistry. We're using a balanced equation, those balanced equations that we've been interpreting, to calculate the quantities needed for a chemical reaction. So how much of each of our reactants do we need to form whatever product that we're trying to form in a chemical reaction? Now, we've been interpreting balanced equations, and that's going to come back into play here. We've been interpreting based on representative particles, on moles, on mass. Moles especially, the interpretations on moles is especially what we're going to see here in what we call a mol-to-mol ratio. So we're going to use those balanced equations and the coefficients in the balanced equations to create a conversion factor that is simply a ratio of moles of one substance to moles of another substance. Okay, so this is the equation that I'm going to use for a couple of examples, actually all the examples today really. 4Fe plus 3O2, oxygen, gives you 2 Fe2O3. Okay, so we're going to be looking at this, and first of all, we need to look at what these coefficients mean. Remember, the coefficients can mean the number of representative particles or also the moles of each of these substances. So we know that there's 4 moles of Fe for every 3 moles of oxygen needed to create or produce 2 moles of Fe2O3. Okay, so these are the ratios that I have down here. If we're comparing just the two reactants, then I have 4 moles of Fe to 3 moles of oxygen, or 3 moles of oxygen to 4 moles of Fe. Goes both ways. If I'm comparing the product to one of these two, I have 4 moles of Fe, right here, to 2 moles of the product. Or I have 3 moles of oxygen to 2 moles of the product. 3 moles of oxygen, 2 moles of the product, or vice versa. Okay, so we're using those ratios today for our stoichiometry, calculating how much of the products or reactants do we need to form a certain amount of the products. Our problem that we're going to start with is how many moles of oxygen are needed to react with 5.42 moles of iron. Okay. Now, the trick, really the key here is, remember that if you have one unit on the top and the same unit on the bottom, moles of the given, if they're the same unit, they cancel each other out, they cross out, and you're left with just the unit that's on top. So here we're going to go with moles of the given on top, the given unit. Moles of the given must be on bottom because that's how they're going to eventually cross out, and moles of the wanted unit will be on top. Okay, so we are starting here with 5.42 moles of iron. That makes 5.42 moles of iron our given. Okay, so 5.42 moles of iron goes on top. The given unit, moles of the given, goes on bottom here. So moles of iron here is here. It also has to go on the bottom because that's how they're going to cancel out. My moles of the wanted, which in this case is oxygen, are going to go on top. So moles of oxygen on top. Now all I have to do is use this balanced equation and the coefficients I see there to plug it in to make my mole-to-mole ratio. So moles of oxygen, 3 moles of oxygen. Moles of iron, I see, is 4. Okay? So 5.42 moles of iron. Moles of iron is on top and bottom, so it crosses out. I multiply everything across the top and I divide by everything on the bottom. So 5.42 times 3 divided by 4 is going to give me 4.07. And my unit that I'm left with here is moles of oxygen. Now, this mole-to-mole ratio is the only way to go from one substance, iron here, to another substance, oxygen here. In this one, I'm trying to go from, again, moles of iron to moles of Fe2O3. In order to get from one substance to a different substance, you need that mole-to-mole ratio, okay? So let's try another example. Let's figure out how many moles of Fe2O3 will be produced with the same starting moles of iron. So moles of iron is on top, therefore moles of iron must be on bottom also. That's how they're going to cancel out. And on top is, again, mole-to-mole ratio, moles of my wanted. I'm trying to find Fe2O3. So Fe2O3 goes up here, and I look at my balance equation for the ratio. How many moles of Fe2O3? 2. How many moles of Fe? 4. Okay. Again, moles of Fe is on top and bottom, so it crosses off. And we're left with moles of Fe2O3 here. We just need to calculate 5.42 times 2 divided by 4, and we get 2.71 moles of Fe2O3. Okay? So these are more basic stoichiometry problems where you have moles as a given and a wanted. Both the given and the wanted are moles. What if that's not the case? Well, we can still use stoichiometry, and we will for sure, if moles is not part of either or both the wanted or the given. In this case, we're going to have to do a couple extra steps to figure out the product formed. Okay, so we're going to use what we just learned, that mol-to-mol ratio, to convert from one substance to another. Remember, the only way to go from one substance, like Fe, to another, like Fe2O3, is that mol-to-mol ratio. That's the step that gets us from Fe to Fe2O3. We're also going to need to use what we learned last time, which is that mole island or mole highway, to convert from one unit to another. Okay, so this is our mole highway down here. Let's say I have mass of A. To convert from mass of A to moles of A, I'm going to use that mole highway. To actually get into another substance, this is why ... we're going to go to moles of B, and then we can use the mole highway to get to any of these, volume, mass, or particles. The key here is you have to go to moles first. It doesn't matter what you're starting in. Go to moles first, then use the mol-to-mol ratio, and then you can convert back out to whatever unit you're looking for. So remember, go to moles first. We're going to have to use this conversion factor, or equivalency statement that we've seen already. Remember, 1 mole of any substance is equal to Avogadro's number of those particles, is equal to the molar mass, right? Those are really what we use most. And we'll get into 22.4 liters of a gas at STP is also equal to 1 mole, 6.02 times 10 to the 23rd particles, molar mass, right? These are all equal to each other, okay? Here's my balanced equation again, so let's try out this problem. If 6 grams of iron reacts with excess oxygen, how many grams of Fe2O3 would be produced? Okay, I'm not starting in moles, and I'm not going to moles. That means I still have to go to moles first, okay? So my first step needs to be getting from grams of Fe to moles of Fe, okay? Grams of Fe is on top, so grams of Fe is on bottom. I'm trying to get to moles of Fe first. So moles of Fe is my first wanted unit. This is where my molar mass comes into play. And 1 mole of Fe, what's the molar mass of iron? It's 55.85 grams of Fe, right from the periodic table. And now, grams of Fe is gone. My new given unit is moles of Fe. So again, this unit needs to go on bottom here, because that's how it's going to cancel out. Moles of Fe. Okay, so I just got into moles. Now I can do that mol-to-mol ratio. So I know moles is going to be on top and bottom. So this is going to need to be the moles of my wanted unit. I'm trying to get ultimately into grams of Fe2O3. So we're going to start by going to moles of Fe2O3. And now I need my balanced equation for the mol-to-mol ratio. How many moles of Fe2O3? 2. How many moles of Fe? Right there. 4. And those are what the coefficients are telling us, okay? Again, moles of Fe is on top, moles of Fe is on bottom. They cancel out. The whole point of this is to cancel out those units. It has to be on top and bottom, and we're strategically setting it up that way. Now, my new given unit is moles of Fe2O3. So again, that given unit needs to go on the bottom here. Moles of Fe2O3. Now I'm already in my new substance. I've already gone from Fe to Fe2O3 with that mol-to-mol ratio. Now, okay, we jumped over here, mole of substance B. Now I can use that mole highway to kick back out to mass, okay? So this is going to be grams of Fe2O3. And again, that molar mass is going to come into play. In 1 mole, it's always 1 mole, unless it's the mol-to-mol ratio, it's always 1 mole, okay? So, in 1 mole of Fe2O3, what is the mass of Fe2O3? Okay, so what's the molar mass of Fe2O3? You add it up from the periodic table, 2 irons, 3 oxygens, and you get 159.70 grams of Fe2O3 for each mole of Fe2O3. Again, moles of Fe2O3 cancel out here because that unit is on top and bottom. And all we have left to do is multiply everything across the top, divide by everything across the bottom. So 6 times 2, well 6 times 1, 6, times 2 times 159.70, divided by 55.85, divided by 4, divided by 1. Okay, so we get 8.58 grams of Fe2O3. That's the unit that we're left with, grams of Fe2O3. So if I start with 6 grams of iron, that's how much of that reactant I have, I can form 8.58 grams of Fe2O3, assuming I have enough oxygen, which right here we find out we have excess oxygen. We got plenty of oxygen to make this reaction happen. So with 6 grams of iron, you can form 8.58 grams of Fe2O3. Right, now let's take a look at what this excess oxygen means. When you're baking cookies, this is our limiting reagent and percent yield. Very brief. When you're baking cookies and you have 3 cups of flour, 6 eggs, and 3 cups of sugar. Well, our recipe, I made up a recipe, calls for 3 cups of flour. Oh great, that's what we have. 2 eggs, oh, we got 6, we got plenty of eggs. 1.5 cups of sugar, we got 3 cups of sugar, plenty of sugar, okay? So what is limiting us in how many dozens of cookies we can make? What's limiting us is that we only have 3 cups of flour. So that 3 cups of flour is our limiting reagent. Okay? That's the one that's limiting how many dozen cookies we can actually make. So what we call this is it's the reactant that is used up completely. Once we make 1 dozen cookies, all those 3 cups of flour are going to be used up completely. And that actually determines the amount of product we can produce. We don't have more than 3 cups of flour, so we can't make more than 1 dozen cookies. Here, we've got plenty of eggs, we've got plenty of sugar. In fact, triple the amount of eggs we need and double the amount of sugar we need. These are both then excess reagents. They are the reactants that are not used up. There's going to be some left over when the reaction stops. When the flour runs out, there's going to still be eggs and sugar left over. Okay? Same idea with chemistry. When one reactant runs out, there's still going to be some left over, probably, usually, of the other reactant. It's very rare that they would both be used up entirely. Okay? So one will be the limiting, one will be the excess. All right? When we're looking at these, we're going to use calculations to figure out the percent yield. So what percent of the product have we formed based on what we expected to form? And we use this equation to actually calculate the actual yield divided by the theoretical yield. So the actual yield is in the lab what you actually produce of the product. How much, what quantity of the product do you produce? So what quantity of Fe2O3 is produced? Divided by the theoretical yield, which is stoichiometrically how much we think we should produce. Okay, so from here, with 6 grams of iron, we think we should produce 8.58 grams of Fe2O3. So we compare what we think we should produce based on stoichiometry to what is actually produced in the lab. Okay, so here's an example. It's pretty straightforward. If 8.25 grams of Fe2O3 is produced in the lab, so let's say we do this experiment and that's what is produced, what is the percent yield for the previous problem, so the one we just looked at? Well, the actual yield, the lab yield, is 8.25 grams. Now we're going to do a lab where we actually run a reaction and see how much of the product we produce and then compare it to how much stoichiometrically we should have produced, all right? So either you're going to do this in the lab or you're told this is what's produced in the lab. So 8.25 grams is produced in the lab. 8.58 grams is what we expected to produce, right? That's the theoretical yield. Divide those and multiply by 100, and that'll give you what percent of 100 did you actually produce? What percent of the full amount that you should have produced did you actually get? And in this case, we get 96.2%.